What I'm going to do, I would like to talk about solar energy a bit. I want to talk about energy in general, and I thought, what can I possibly do in 10 minutes? And so usually there's a tendency of people here to talk about their own research, and I thought maybe in 10 minutes I'm going to fail miserably on that. So I thought maybe I tell you my honest opinion about what should be done energy-wise in the world, because as Evelyn showed earlier, we are going to destroy our planet. And we're doing that at a quite nice rate. And the funny thing is that nobody seems to care, including myself, because there's a big difference between hearing about that, saying, yes, that's true, and about changing something. So anyway, what I'd like to obviously this is incomplete, but I try my very best in the given time frame. So the first thing is, I was actually quite shocked to see that within this university, we had a meeting 3, 4, 5 years ago, and there were people, educated people, who were disputing that there is a greenhouse gas problem. So people said, oh, look, there are huge differences in the intake and outtake CO2 from the oceans into the oceans, and the little bit human mankind is adding is just negligible. To the best of my opinion, I can tell you this is a blunt lie. So what we're actually doing, and this is actually nicely correlated with the data, this is the carbon dioxide in the world, as this graph shows, and this is really just against years here. So this is just 1000 AD, this is where we are at the moment, so this is a quite older graph because it gets worse and worse. And what it shows is the amount of CO2 you can find, and then somebody could ask me, okay, and where did you get the data from 1,000 years ago? The point is that people used ice. They looked how much CO2 is frozen into the ice, and you can analyze this quite nicely. And you see that this curve, does it have an inbuilt laser even? Doesn't explode, doesn't explode. The middle one, maybe? I fear it explodes here. Oh yeah, thank you, it's fine, it's fine. So I can show a bit better where I am if I do that. So this is obviously the graph of the CO2, and if you just look for the past 400 years, this is the evolution of the CO2 as found, for example, trapped in ice cores. And this straight line is actually the invention of the steam engine from James Watt. And you see there's a direct impact on industrialization. Actually, you see even little things in the CO2 production when technology is changed. So there's no doubt about that the CO2 is a problem, and they were actually burning too many fossil fuels here. And let's just look, what are we consuming on a daily basis? And this is actually something which is always a bit difficult. So a car would use up something like 40 kilowatts hours per day. I've kept that, actually, this is from David McKee from Cambridge. I kept it in the unit which you will find on your meters regarding your energy consumption, your electricity consumption, for example, from EBS. So the car, this is what you do if you drive 40 kilometers per day. So if you travel from Bray to Dublin back and forth on a daily basis, or go on holiday with your car from time to time, this is the average you're going to use. And the next thing is jet flights. Jet flights, this here is your energy you're wasting using a single flight to Cape Town per year. A single flight to Cape Town. And this amounts roughly, same order of magnitude, to the whole energy you're using if you drive the car for a whole year. And there are other things, heating and cooling, this is on the same scale, by the way. And we have other things, I had to offset that a bit. This is actually production of goods we're using. So the goods we're using need to be produced somewhere. Food, gadgets, light, transport, and defense. This is the average values actually coming from a neighbor island. So these values are quite valid for Ireland because Great Britain is very similar. It's similar in climate, it's similar in location on the Earth, it's similar in latitude and longitude. And the question is now, can we produce enough energy from regenerative sources? And the answer would be maybe, because we can, but the effort is too high. But let me just show what a potential scenario for this is. So a potential scenario, energy production, what we could do. What we do already a bit, this is not what we have. This is what could be done at maximum. So this is wind, 20 kilowatt per hour, kilowatt hours per day. Solar heating, just having solar panels on your roof. This is PV on your own roofs. This is PV farms. This is biomass food and biofuel. This is what you can get maybe realistically at maximum if you fill something like 10% of the whole country with windmills and solar. This is a huge amount. And This is what you can additionally do: shallow offshore, deep offshore, tidal, and wave. Just politically speaking, it's quite fascinating that we are focusing on a relatively small amount in terms of research funding here in this country, in particular, because that obviously doesn't change the general problems we have in the world or here in Ireland. Anyway, that just gives you a feeling. So this is the extremeness, taking all regen energy you can harvest potentially and try to counter what we're on average using here on the other side. So one message, one take-home message is we need all of these alternative LNG forms. And this is probably, from the financial standpoint, not a realistic scenario. Okay, so anyway, by the way, just to make the point, this orange area is all solar. It's all directly harvested from solar. This is actually wind, and wind is directly derived also from the solar energy. So if you now see what is actually provided, it's actually quite a lot what is provided. This is actually similar to what we have had in a keynote talk. This is the spectrum which we receive in principle. So this is the general average spectrum of the sun. The sun behaves just like something which has a temperature of about 6,000 degrees Celsius. That's the surface temperature of the sun, and then the whole thing is just called a blackbody radiator. And just to make a point, there's one equation. I dared one equation here. This equation is important because when the people tried for the first time to understand what spectral features the blackbody radiator actually has, they stumbled over quantum mechanics. Because here you find in this equation, this H is Planck's famous smallest unit of energy. And you can't solve the equation without postulating that light actually consists of little photons, which are single quanta of energy. Okay, so what do we take from that? It kind of reestablished what has been already said. This is the visible range between here and here, roughly speaking, and the sun has a maximum roughly in the green. There are good reasons to believe that, for example, our eyes are most sensitive to the green, and evolution have made our eyes to be sensitive because this is the classical light source we were used to. Okay, how much energy do we receive? And this is actually also quite interesting. The sun emits 63 megawatts per square meter sun surface. And at the distance in which we are, 150 million kilometers away, so Evelyn said 8 minutes, the light leaves 8 minutes to reach us, it's still roughly about 1.3 kilowatt per square meter. However, this is the total amount of energy radiated. That's not all harvestable, there's no question about that. And this is a square meter above the atmosphere. So obviously, if you have a strong cloud cover, this is not going to work easily. However, what we get is 1.37 kilowatt per square meter, even here in Ireland, if there is no sun, and if you tilt 1 square meter towards the sun. So if it's not grazing incidence, but actually really perpendicular to that surface. So if you just see how much energy do we receive, we get this mind-boggling value of 120,000 terawatts, anytime. Yeah, not here, but somewhere on Earth. The total amount is always that amount. It's either absorbed in atmosphere, partially reflected in fairness, but otherwise absorbed in many, many different forms. And we wouldn't be here if that wouldn't be the energy we roughly receive, because otherwise the whole planet would cool out and would have a complete different temperature. Okay, so the whole total consumption human mankind has, electricity, is about 18 terawatts. And this is just a fraction of the 120,000. Well, this is misleading. This is a bit propaganda I'm doing here because you're not going to harvest the 1-to-1 and not even a 1-to-10. However, what you can do, you can fill the Earth theoretically with 10% efficient solar cells. That's not a problem. Actually, they're all better than this. Typically, you get something like 19 to 20% efficiency. You can go up to 46% in the meantime. It's just too costly. And these black spots represent then the areas which need to be harvested from, on average, over the year. You can make the full climate model and see cloud covering, all the rest. Obviously, they're located in nice spots. And then you receive the 18 terawatts you need. This is a hypothetical thing. The areas look very small on a world map. They are, of course, huge. But you can make them smaller, and nobody says we have to do everything through solar. It's just an interesting point, because it's the only energy form which can deliver that amount of energy. Nothing else can do so. Anyway, so they're just coming to the end. I just see that. Of course, there's a certain interest to improve solar cells. Solar cells, as I said, if you buy them from a big company, you get them roughly at 19-20% efficiency. You couldn't do better. The question is, how good can we theoretically make them? Just as a hypothetical question. And the answer to this is actually, well, we can improve quite a bit. First, what is the problem? One of the problems is the so-called Shockley-Queisser limit. And it's very simply explained because the photons have a certain energy, and the length of the arrow symbolizes just the energy they have. If you have a semiconductor, which is typically the material you use, you have a band gap. The band gap, in order to bring an electron through the whole band gap to the conduction band, so it can be used, you need the energy of the band gap. So photons now have three possibilities. Either they don't have enough energy, so they don't harvest it at all. They can't bridge the band gap. They have the right energy, which is an ideal scenario, but so they can't be harvested. If they have too much energy, what happens is actually that this extended extra energy is lost as well. And then this becomes a very similar and simple idea. If you have a single band gap, you either have too high, too low. So where do you put your band gap? And of course, you put it there where you harvest most of the energy in the realistic way, but not wasting too much. And this is directly correlated with the maximum in the green. Okay, so, but we don't have to stick to single cells. We can use modern nanotechnology, or we can use actually double, triple tandem cells, which then have 2 or 3 different band gaps, and you can harvest actually something around 50%. This just gives you an impression of the different cell types. And this is the world record chart. So the world record chart actually shows you here that you can buy cells, or Fraunhofer actually produce cells at 46% efficiency, which would make the roof harvestable area much smaller than actually necessary. Okay, so a bit of truth on the other side. As we all agree, the sun doesn't shine at night. And not always, I mean, we have learned here where we are, there's mostly sun. On the West Coast, there's no sun at all, if I overdo it a bit. So there are obviously better locations, not so good locations, but also if you just think about putting photovoltaics on your roof, you see that there's obviously the need for storing energy. And this is a problem, no doubt about that. And so energy storage, using the energy at the right moment, smart energy, and energy distribution are important points which have to be considered. Anyway, that's enough for the 10 minutes. So this is a statement of MIT just done in the meantime, 2.5 weeks ago, and which clearly states the only way to actually go forward is to consider solar as a viable source. Not saying that other sources are not viable, but excluding solar is a bit of madness in that regard. Thank you very much.